The first snow always came early to the highlands. By October, frost crept through arrow slits and settled into corners where torchlight couldn't reach. Inside the stone walls of a medieval castle, a servant woke before dawn and began the day's most critical task. Not preparing food, not tending horses, but feeding the fires. He hauled split logs from the woodpile, stacked kindling in the great hearth, and struck flint until sparks caught. The flames would burn continuously until spring. Stopping them, even for a day, meant the castle itself would turn against its inhabitants. Medieval castles were marvels of military engineering. Walls thick enough to withstand siege engines. Towers positioned to rain arrows on attackers. Gatehouses are designed to trap invaders in kill zones. But these same features created a hidden enemy, one that couldn't be defeated with swords or strategy. Stone walls up to 3 meters thick absorbed heat like a sponge drinks water, then radiated cold back into every room. Narrow window slits that protected archers also blocked sunlight and trapped frigid air in circulation. The architecture built to keep enemies out locked the cold inside. The question that faced every medieval lord was urgent and straightforward. How do you survive winter inside a fortress designed to be impenetrable? The problem began with the material itself. Stone has remarkable thermal mass, the ability to store energy, but almost no insulating capacity. During cold months, the massive walls functioned as what engineers call a cold sink. Heat generated by fires, bodies, and daily activity flowed constantly into the stone, cooling the air and chilling anyone who stood near the walls. A castle wasn't just cold. It was actively draining warmth from everything inside it. The thicker the walls and defensive necessity demanded extreme thickness, the more severe the thermal drain became. This drain created a resource crisis that shaped medieval politics and economics. Keeping a castle warm required staggering quantities of fuel. Wood was the primary source, supplemented by peat and charcoal where forests had thinned. But wood is heavy and bulky. Transporting it any distance was prohibitively difficult due to the limitations of medieval carts and roads. Castles consumed fuel from their immediate surroundings, clearing forests in expanding circles. Between the years 1000 and 1300, Europe's population tripled. Agricultural expansion devoured woodland. Simultaneously, military campaigns consumed timber on an industrial scale, building siege towers, catapults, warships, and fortifications. By the 1200s, Britain could no longer supply its own lumber and began importing it from Scandinavia. The fuel to heat a castle became a commodity as valuable as the stone used to build it. This scarcity meant that warmth wasn't simply a matter of lighting a fire. It required a vast infrastructure of labor and control. A castle needed foresters to identify and fell trees, carters to haul logs across miles of rough terrain, servants to split and stack wood, and stewards to manage the entire supply chain. The ability to keep fires burning through winter was a direct measure of a lord's power, not military power, but economic and administrative dominance over the landscape and the people who worked it. A warm castle announced that its lord commanded enough resources to feed a structure that consumed fuel like a starving animal. Medieval builders responded to this challenge not with a single invention, but with an evolving system that revealed an increasingly sophisticated understanding of thermal physics. The earliest solution was the open central hearth. In the Great Hall, the social and political heart of the castle, a circular or octagonal hearth sat in the middle of the floor. It was built from stone, brick, or tile and burned continuously. Smoke rose toward the ceiling, lingered in the rafters, and eventually escaped through openings in the roof, simple holes, louvres, or unglazed gable windows. The central hearth was inefficient. Smoke filled the hall, stinging eyes and blackening walls. Heat radiated outward but dissipated quickly into the vast stone volume. Drafts from doors and windows scattered warmth before it could accumulate. Yet the hearth persisted into the Tudor period, centuries after better technology existed. The reason was cultural, not technical. The fire in the center of the great hall was the physical and symbolic core of the household. It defined social structure by proximity. Nobles sat closest, basking in warmth and light, while servants and soldiers occupied the drafty periphery. The hearth was where oaths were sworn, disputes settled, and feasts held. Moving the fire would mean abandoning the symbolic center of feudal life. But in private spaces, efficiency mattered more than tradition. The revolution came when builders moved fire against a wall and learned to control smoke. Early attempts used lightweight materials such as wattle and daub over timber frames and plastered them for fire resistance to create hoods that funneled smoke upward. These hoods collected combustion gases and directed them out of the living space, improving air quality even if they didn't significantly increase heat retention. By the late 12th century, this system had been integrated into the stone structure itself. The mural fireplace was born. Fire burned in a recess built into the wall. Above it, a stone funnel narrowed into a flue, a vertical shaft that climbed through the wall's thickness, sometimes spanning multiple floors. The term chimney referred collectively to the entire system, including the hearth, mantel, flue, and external stack. Building these systems required precision masonry. At Schönberg Castle, constructed in 1201, the chimney flue crosses diagonally through walls nearly 3 meters thick. The cuts had to be exact. Misalignment would allow smoke to seep into adjacent rooms or create dangerous backdrafts. The narrowness of some early fireplaces suggests that wood was stacked vertically to maximize heat output from limited space, a detail that reveals how constrained builders felt by both fuel scarcity and the thickness of the walls. The impact of the chimney was immediate and profound, but not where modern observers might expect. Chimneys didn't spread through great halls. They appeared in private chambers, the solar, the king's wardrobe, the lord's personal apartments. Royal records document this pattern explicitly. In 1229, King Henry III ordered new chimneys for the Great Chamber at Havering. Orders for chambers at Kempton and Winchester followed quickly. The solar, typically located on an upper floor above the Great Hall, became the refuge where the lord and his family could escape what one historian described as the bustling communal living below. The chimney was a technology of privacy as much as it was a source of warmth. It allowed the aristocracy to separate themselves from the household, to retreat into spaces where heat was localized, smoke was absent, and comfort was assured. This separation wasn't subtle. It was an architectural enforcement of social hierarchy. The lord enjoyed clean air and radiant warmth in his private chamber, while servants and soldiers continued to endure the smoky, drafty great hall. The cost and expertise required to build chimneys limited their installation to spaces occupied by those with power. Thermal comfort became a visible marker of status. But the true genius of medieval castle heating wasn't the chimney. It was the walls themselves. Stone, despite being a poor insulator, is an exceptional thermal battery. During the day, when fires blazed in hearths and chimneys, the massive walls absorbed heat. This wasn't a flaw. It was the foundation of the entire survival strategy. The absorbed energy wasn't lost. It was stored. As night fell and fires were banked or allowed to die down, the stone began releasing this stored heat back into the rooms. The process is called thermal lag, and in a castle it could last 10 to 12 hours. This delay was critical. The coldest hours came just before dawn, long after the day's fires had diminished. But those were precisely the hours when the stone walls, still warm from the previous day's heating, radiated energy back into the frigid interior. The walls transformed from enemy to ally, providing what engineers today call thermal inertia, resistance to temperature change. The castle didn't stay warm because fires burned all night. It stayed warm because the structure itself had been preheated during the day. Medieval builders understood this principle intuitively. They didn't build thin walls with insulation. They built thick walls that could absorb and store massive amounts of energy. The stone fireplace itself, often enormous in scale, functioned as a thermal battery. At Rochester Castle, the fireplaces were deliberately oversized to maximize this storage effect. Modern analysts refer to this phenomenon as stone memory. The walls also provided radiant heat rather than convective heat. Convective heat warms air, which then circulates through a space. But air is light and mobile. In a drafty castle with high ceilings and constant air exchange through doors and window slits, convective heat was nearly useless. It escaped almost as quickly as it was generated. Radiant heat, by contrast, warms objects and people directly. It doesn't depend on air temperature. A person standing near a stone wall that has absorbed a day's worth of fire heat feels warmth penetrating their body, even if the air around them is cold. This is why radiant systems provide what thermal comfort researchers call deep comfort, a sensation of warmth that persists and satisfies in ways convective heating cannot match. The castle's design reinforced this strategy through carefully calculated architectural details. Window openings were shaped with extreme precision. Externally, they were narrow, sometimes only 4 inches wide, to minimize the penetration of cold air and provide defensive cover for archers. But internally, the openings splayed outward, widening significantly to let in maximum light and provide room for defenders to maneuver. This funnel shape had a secondary thermal function. It reduced the velocity of incoming cold air, diminishing drafts while still allowing ventilation. The window wasn't just a defensive feature. It was an integrated component of the castle's thermal management system. Yet even with thermal mass and architectural refinement, the stone structure alone couldn't provide adequate warmth. Medieval inhabitants deployed a second layer of defense: material culture. Tapestries transformed castle interiors. They weren't decorative luxuries, though they were indeed beautiful. They were functional insulation. A tapestry hung several inches away from a stone wall created an air gap, a buffer zone where cold radiating from the stone was intercepted before it could reach the room's interior. This gap reduced convective heat loss by approximately 40%. The economics of tapestry production reveal why only the aristocracy could afford this solution. A skilled weaver required a whole month to complete a single square meter of tapestry. Insulating the walls of a central chamber required dozens of square meters of compressed labor condensed into fabric. But this investment was portable. When a lord moved between his estates, and medieval nobility were constantly itinerant, traveling between properties to manage their holdings, the tapestries traveled with them. Thermal comfort became mobile, a capability that could be deployed wherever the lord established his court. For those without wealth, survival required different strategies. The vast majority of a castle's population, servants, soldiers, and lower-ranking household members, relied on communal warmth. They slept together on the floor of the Great Hall or in barracks. Male servants and courtiers bedded down in groups, sharing body heat through the coldest hours. This wasn't optional. It was the only way to survive in spaces where localized heating was absent and architectural mass provided only baseline thermal retention. Even those with access to private chambers used personal thermal technology. The canopy bed, ubiquitous in medieval sleeping quarters, functioned as a miniature insulated envelope. High wooden sides and heavy draped textiles created a small, enclosed space. The sleeper's body heat, which would usually radiate out into a cold room, was trapped inside the textile enclosure. The canopy bed was, effectively, a tent pitched inside a stone box, a final layer of thermal defense. This layered approach, architectural mass, localized fire, textile barriers, and social organization, demonstrates that castle heating was never a single technology. It was an integrated system where each component addressed a specific aspect of the thermal challenge. But even this system had limits. In the coldest regions, where fuel was scarcer and winters more brutal, medieval engineers developed solutions that surpassed anything built in Western Europe. The heat storage Hypocaust represented the pinnacle of medieval thermal engineering. The system derived from Roman antecedents, the Hypocaust, which circulated hot air beneath floors and through walls. This technology hadn't disappeared with the fall of Rome. It persisted in the Byzantine Empire and was reintroduced to Western Europe through Arab architectural influence, visible in structures like the Alhambra Palace. The medieval adaptation was more sophisticated than its Roman ancestor. The heat storage Hypocaust used an underground furnace upon which massive granite stones were piled. Hot combustion gases heated these stones to extreme temperatures. Once the stones reached thermal saturation, vents were opened to allow the stored heat to radiate into rooms above. The system could maintain warmth for days from a single firing. This technology proliferated in the Baltic region, specifically in Old Livonia, which encompasses modern Estonia and Latvia, where winter conditions necessitated extreme efficiency. By the late 15th century, an estimated 800 to 1,000 heat storage hypocausts were operating across the region. They weren't limited to castles. Monasteries, public buildings, and even modest craftsmen's houses in cities like Tallinn featured these systems. In Tallinn, the Hypocaust was standard, not exceptional, a testament to how environmental pressure drives technological refinement. The most advanced example stood at Malbork Castle, the fortress headquarters of the Teutonic Order in Poland. Malbork featured a complete centralized heating system with ductwork channeling hot air into various chambers, a medieval precursor to modern HVAC. In 1822, experimenters tested this 400-year-old system. They burned 7/10 of a cubic meter of wood for 3.5 hours. The system kept the enormous banqueting hall, 850 square meters, warm for multiple days. This level of efficiency eclipsed most modern forced air heating systems. The secret was the labyrinthine path combustion gases traveled through the massive stone structure. Instead of venting smoke immediately, the system forced gases through a complex network of channels and baffles. Every twist and turn extracted residual heat into the thermal mass. By the time smoke emerged from the chimney, existed across Eurasia, it had been stripped of nearly revealing all parallel innovation. The fire itself similar environmental pressures, fast and clean, maximizing combustion efficiency. The Russian pech, while the structure absorbed the Korean and stored the liberated energy on identical release over days, maximized heat extraction through extended contact between combustion gases and thermal mass. The Russian stove, which emerged around the 15th century, integrated cooking, drying, and heating functions. Some designs included sleeping platforms atop the unit, where occupants could rest directly against the warm masonry. The Korean ondol dates back 5,000 years, using cooking fires to heat stone slabs beneath floors, a dual-purpose system that eliminated the distinction between food preparation and thermal management. These technologies were not secrets, but were responses to necessity. In Western Europe, where winters were milder and wood more accessible, castles could afford the inefficiency of open hearths. The sheer quantity of available labor and fuel compensated for poor thermal design. But in regions where fuel was scarce and the cold was more severe, inefficiency meant death. Engineers in these areas were compelled to devise solutions that extracted maximum energy from minimal fuel. The result was technology that modern architects are only now beginning to appreciate and replicate. The contrast exposes an uncomfortable truth about medieval heating. Efficiency was not universally prioritized. The most effective systems, those achieving multi-day warmth from single firings, were restricted to regions facing existential cold or to the private chambers of the elite. The broader castle population continued to endure drafty, smoky, inadequately heated spaces, not because better solutions didn't exist, but because distributing those solutions wasn't a priority. Thermal comfort, like food quality and living space, was allocated according to social rank. This allocation was neither accidental nor invisible. It was enforced through architecture and ritual. In the Great Hall, the location of the fire was the center of social theater. Lords burned massive logs on oversized fire dogs, demonstrating their command over fuel supplies. The scale of the fire announced the lord's power, his ability to command the labor and resources necessary to sustain continuous combustion. Seating arrangements made the hierarchy physical. Nobles occupied chairs and benches closest to the hearth, bathing in warmth and light. Knights and higher-ranking servants positioned themselves in the intermediate zone. The lowest ranks, field workers, scullions, stable hands, stood or sat at the hall's edges, where drafts from doors and windows created pockets of bitter cold. Proximity to heat was proximity to power. The fire didn't just warm bodies, it illuminated the structure of feudal society. The hearth also carried symbolic weight that extended beyond its physical warmth. Before the spread of Christianity, the hearth was associated with household gods and protective rituals. It represented continuity, the unbroken line of family and lineage. As Christian doctrine displaced pagan practice, the hearth retained its sacred quality but acquired new meanings. It became the site where Christian virtue was taught and reinforced, where stories shifted from myths of ancient heroes to narratives of saints and divine authority. The fire remained the cultural center, the place where the household's identity was forged and maintained. This cultural centrality explains why the Great Hall retained the inefficient central hearth even after chimney technology became available. Moving the fire to a wall would have been technically superior, with less smoke, better heat retention, and cleaner air, but it would have destroyed the symbolic function. The visible, open fire in the center of the hall was necessary for political theater. It allowed the lord to demonstrate generosity by gathering his household around the flame. It created the visual and experiential focus for feasts, judgments, and oaths. Efficiency was irrelevant. The fire's purpose was to manifest authority. Meanwhile, the lord's private chamber featured the most advanced heating technology available. A mural fireplace with an integrated stone chimney, supplemented by tapestries that reduced heat loss by 40%. The chamber was strategically located on an upper floor, directly above the Great Hall, where it could capture rising convective heat from the bustling public space below. The lord enjoyed layered thermal protection, architectural, technological, and positional, which was categorically denied to the people who maintained it. This disparity required continuous labor. Servants woke before dawn to rekindle fires. They hauled wood, cleared ash, and tended flames throughout the day. They slept in the coldest spaces, often the great hall floor after the evening fire had burned low, and rose to restart the cycle. Their discomfort subsidized the lord's warmth. The castle's thermal system, like its agricultural and military systems, functioned through the extraction of labor from those with no power to refuse. The ultimate cost of this system was measured not just in human effort, but in ecological destruction. By the 13th century, forests across Western Europe were visibly depleted. Timber imports from Scandinavia supplied Britain's construction needs. Fuel costs rose. Regional shortages became chronic. Yet castle lords continued to burn enormous fires as displays of wealth, consuming resources at rates that couldn't be sustained. The question that medieval society never adequately answered was whether this wastefulness was necessary. The existence of heat storage hypocausts and masonry stoves
corsets for
proved that
warm that
alternative
used the
approaches
after
were
heating
possible.
system that
These
gauged the
systems
steam
achieved superior
400-year-old
thermal
system.
performance with a
They
fraction
burned
of the fuel.
7/10 of a cubic
But
meter
they
of wood
required
for free.
initial investment in
And
skilled masonry and sophisticated engineering.
For 3.5
distributed
hours, the
warmth
hearth
more
roared
evenly,
and whispered,
which meant
every
the lord's
log
chambers
giving up
wouldn't
its
be
heat.
dramatically warmer than the
Then we
servants'
pulled
quarters.
back to see what that heat was
And they
tasked with.
operated on
An
principles of
850 square meter
efficiency
banqueting
that
hall.
conflicted
Stone
with the
columns,
political
timbered
logic
arches
of
rose upon
conspicuous
rows of
consumption.
tables.
2 full days after the
castle
fire was
heating
out,
system,
the Great
in the
Hall
end,
stayed cozy.
was not
just
primarily
warm,
an
comfortably,
engineering problem.
sweater off warm.
It was
That
a
single
political
heating
choice.
session outperformed most modern
Medieval
four-stair
builders
systems, which
possessed
lose
the
their
knowledge
warmth
to
within
create
hours.
efficient,
Look at that thermal profile. It's still
egalitarian
glowing like a...
thermal
Was the labyrinthine path
They
combustion
chose
gases
instead
traveled
to
through the
build
massive
systems
stone
that
structure.
reinforced hierarchy,
Instead of venting smoke,
making
the
warmth
builders guided it
scarce
through a
and
twisting
allocating it
gauntlet of
according to
channels and
rank,
chambers,
which
extracting
turned
every
winter
scrap of
survival
heat before
into
it
a
escaped.
demonstration of power.
Immediately,
cold that
the
servants
system forced
endured was not
gases
an
through a
unavoidable
complex network
consequence
of
of
channels
medieval
and baffles.
technology.
Every twist
It
and
was a
turn
policy
stole more heat,
enforced
delaying
through
their
architecture
escape and
and
wringing out
maintained
every
through
degree of
economic
energy.
control.
The labyrinth glowed like a
When
living
we
circuit,
examine
a
medieval
deliberate
castles today,
Each twist
we
pulls
see the
more energy
fireplaces,
from the
the
gases,
chimneys,
pressing it into the
and
stone.
massive walls.
The heat soaks through the masonry,
We marvel
building
at
a
the
reservoir of
craftsmanship
warmth
and
inside the
ingenuity.
thermal mass. By the
beneath
time
the
smoke
stone
finally
and mortar
escapes the
lies
chimney,
a harder
most
truth.
of the fire's power has
The
already
most
been put to work.
sophisticated technology
It had been
was
stripped of
reserved
nearly
for
all
those
its
who needed
energy.
it least.
The fire itself could
At the
burn
same
hot,
time,
fast.
those who labored to
What
sustain
remained
the
was
system
pure efficiency.
survived.
Heat
through shared
captured,
body
waste
heat
minimized,
and
and
communal
only a
suffering.
cool breath of smoke left
The
to tell the
castle was
story.
warm at its center and cold at
and
its
clean,
edges.
maximizing
And this gradient
combustion
was not a
efficiency,
design
while the
flaw,
structure
but
absorbed
rather a
and stored the
deliberate
liberated
design
energy
choice.
for gradual release.
The story
Every
of
stone,
medieval
pipe,
castle
and panel
heating
worked
is,
in harmony,
ultimately,
turning a moment
a
of
story
burning
about
into
who
hours
deserves
of gentle
comfort
warmth.
and who decides.
International
It's about the
release over
difference between
days.
what humans can build
Similar systems
and what they
existed
choose
across
to build.
Eurasia, revealing parallel
walls could
innovation
store
driven
heat
by
for 12
similar
hours.
environmental needs.
The Hypocaust could warm a hall for 3 days on a single firing. The tapestries could
There's
cut heat
pressures.
loss by 40%.
The Finnish kakalun, the Russian
However,
pek, and the
these
Korean ondol
capabilities were
all
deployed
operated on
selectively
identical
and
principles.
carefully,
Capture the fire's heat,
ensuring that
steer it through
warmth
channels of
remained a
heavy
privilege
mass,
rather
and let
than
the
a
stored
right.
warmth radiate long
In the
after the
coldest
flames go
months,
out.
when snow
tiles-
drifted
Pacific
against the
maximized
outer
heat
walls,
extraction through
and
extended
frost
contact
crept
between
through
combustion
arrow
gases
slits.
and thermal
The
mass.
castle's
The Russian
interior
stove,
became a
which
map
layers
of
labyrinthine
power.
flues inside
Every
a
degree
massive
of
shell of
temperature
masonry,
marked
holds
who
onto the heat
commanded
long
and
after
who
the fire
obeyed,
fades.
who
The
slept
gases
warm
travel a
and who
winding
did not.
path, each